So note down yesterday's problem. So that the function f of z is equal to square root of mod xy is not analytic at the origin, even though CR equations are satisfied. Not analytic at the origin, even though CR equations are satisfied. So does anybody tried this problem? So anybody got the answer? So does anybody prove that it's not analytic? So other than Kavya? Okay, so let us see. See this, the function f of z is equal to square root of mod xy. This is the function. And for this function, the CR equations has to be satisfied. That is, dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou x. So these are the CR equations. Now these CR equations needs to be verified for this particular function. At the origin, he said. Now at the origin we mean here this can be written as u of x comma y plus I times of v of x comma y. So, or in other words, this is square root of xy mod plus I times of 0. That means v is a 0 function. Got it? Yeah. So now actually here dou u by dou x we need to be finding it out. Dou u by dou x is nothing but limit x tends to 0, u of x comma 0 minus u of 0 comma 0 divided by x. Is this correct? Whatever I have written, is it correct or not? Is this correct or not? Here actually I have not used delta x, instead I used x, y. No? Not just because it is a real value. Kavya, can you tell me why I have used x instead of delta x? This will be very big confusion, because even in the upcoming classes also I am going to use the similar manner. Anybody has any idea on this? No, not because x is defined. Here the fundamental reason why we are using x rather than delta x is, here in this particular case delta x is equal to x. This is the reason why we are using. Why delta x is equal to x here in this case? Why? Because see this in the problem statement, show that the function f of z is equal to square root of mod xy is not analytic at the origin. So this is very, very important. At the origin. So at the origin we mean we are trying to verify the function at the origin. Now from the origin, if I take any value, an elemental distance here actually if I consider this distance, this is nothing but delta x. Delta x is located at a distance of x from the origin, correct or not? So even if I take the delta x on the negative side, this is delta x, again this is x. So that is the distance from the origin to the point of consideration is always equal to x. This is exactly the reason why we use delta x is equal to x for our analysis purpose. The simple reason is we are considering the point at origin. Here delta x is equal to x because delta x is equal to x minus 0. This is x. Understood now? Understood or not? Because this is very important to understand. So now actually, if you put forward these values, this is u of x comma 0. So that is y value is 0. So this is 0. Then this is 0 minus 0 divided by x. This is equal to 0. And then similarly, dou u by dou y. This is limit y tends to 0. U of 0 comma y minus u of 0 comma 0 divided by y. Here u of 0 comma y 0 comma 0. Why? Because we are trying to identify the limit at this point. That is the derivative we are trying to check at origin. That is the reason we are taking the difference between two different values of the function. That is u of x comma 0 minus u of 0 comma 0 divided by x. So this is ideally 0 plus delta x divided by delta x. Limit delta x tends to 0. Rather than putting delta x, we have replaced here x and here also x. As simple as that. Got it? So this is also 0. Because u of 0 comma y, if you put it here, x value 0 and whatever may be the value of y, it will be 0. So 0 minus 0 divided by y, this is again 0. Similarly, dou v by dou x. So dou v, so this is limit x tends to 0, v of 0 comma x, v of x comma 0 minus v of 0 comma 0 divided by x. So this is v is anyway 0 because this value is 0 and v of 0 0 is anyway 0. This is also 0. Similarly, dou v by dou y is also equal to 0 because y is anyway 0 function. Hence, the CR equations all are being 0. The CR equations are getting satisfied. Got it? So the CR equations are getting satisfied. Hence, ideally, if the CR equations are getting satisfied, the derivative should be exist. Correct or not? Got it? So here, it's not that if the CR equations are getting satisfied, you will always find a derivative. Because the CR equations are nothing but the minimum mandatory requirements for a function to be derivative to possess, right? So these are the minimum required conditions. So if we just take the minimum conditions, we are not very sure that whether the function is having derivative at that point or not. That's why in certain cases, there may be a failure. We mean you are trying to check only the minimum possible conditions. There might be a condition where the condition might fail, right? So that's why even though the CR equations are satisfied, in certain cases, we don't know whether the derivative exists or not. These are certain cases like that. Got it? So similarly, if you want to find out the derivative, limit z tends to 0, f of z minus f of 0 divided by z. So this is the derivative. Again, we are writing this f of z minus f of 0 divided by z. Why? Because f of z is nothing but f of 0 plus delta z minus f of 0 divided by delta z. Limit delta z tends to 0. That is how actually we derive the definition of derivative, that is df of z by dz. Got it? Understood or not? Now this derivative, so along x-axis anyway you can check this condition to be 0 and along y-axis also fine. Now actually along a random direction, limit y tending to x, so y is equal to mx line and then x tends to 0, f of z minus f of 0 divided by z. So if you try to approach in this format, right? So z is nothing but x plus iy. Why we are trying to approach this format is, see this, we are trying to find out the limit value at the origin. Now actually this can be approached in all the different directions. Now one random direction what I am considering is this direction, wherein y is equal to mx and then x tending to 0. That means I am trying to approach the 0 value along the line. Got it or not? Do you have any questions? I hope you understood clearly. Yes or no? Can somebody confirm? I hope everybody is on pace. Okay. Now actually, so if you put this format, f of z is nothing but square root of xy minus f of 0 is 0 divided by y is equal to mx and x tends to 0 and this is x plus iy. This is y if you replace with the mx, then this is root m into x divided by x into 1 plus m into I. This x will cancel and then anyway, so this limit y is equal to mx and x tends to 0 will be equal to root m divided by 1 plus im. Now if you notice, this value is f of z derivative. This is dw by dz is coming out to be a dependent function on m. Now for each value of m, the value of the derivative is different, which essentially means that the derivative doesn't exist, or the limit value of limit delta z tends to 0 f of z plus delta z minus f of z divided by delta z is not exist. That means the derivative is not exist at the point of origin. Got it or not? So, but at the origin we verified that the CR equations are getting satisfied, but still there is no possibility of the existence of derivative because this is the derivative value is dependent on m, which is not unique. Got it? Hence, though the C, okay, you note down this. Hence, though the CR equations are satisfied, the derivative doesn't exist at origin. That means origin is a singular point. Got it? So you can note down this. Yeah, so m is always a real number. M is a slope. Slope can't be a complex number. Note it down. Okay. So exactly in the similar lines, I'll give you one more problem, I think which was given in the previous years. So you can solve that now. Same procedure, no change. Prove that the function f of z defined by, prove that the function f of z defined by f of z is equal to x cube into 1 plus I minus y cube into 1 minus I divided by x square plus y square. This is the function. So this function is defined if z not equal to 0 and this value equal to 0 if z equal to 0. This is the function, it was defined. Is continuous and the Cauchy-Riemann equations are satisfied. Is continuous. You have to prove whether this function is continuous or not. And CR equations are satisfied. At the origin, till the derivative doesn't exist. Can you prove this? I'll give you 5 minutes time to try to prove this. I didn't get your question, Kavya. How to know when to stop only finding at point and when to continue? I didn't get that. Can you reframe your question? So others can try solving this exactly in the similar manner. See this, Cauchy-Riemann equations are the bare minimum conditions for the function derivative to exist, right? Now, this is only the trial and error basis. So, usually, right, we check only three different ways. Usually, that's what we do. One is delta x tending to 0 and delta y tending to 0 and y is equal to mx and then delta x tending to 0. So these are the conditions, bare minimum conditions that we are going to use usually for finding the derivative, right? So usually y is equal to mx case, if it is dependent on m, then actually we say that the function derivative doesn't exist. Or else actually we can say that it is derivative exists, but we are not 100% sure. But around 99% we are sure that the derivative doesn't exist. But there is no hard and fast rule to say that the derivative mandatorily exists or mandatorily doesn't exist. So we are checking only the bare minimum conditions, but 99% of the cases, if these derivative limits are equal, then the derivative usually exists. The failure case is only this, most of the cases, even in this case also. Last is delta z tends to 0. The same thing, limit delta z tends to 0, f of z plus delta z minus f of z divided by delta z. This is what is the derivative, right? So, in this derivative, what we usually do is, at z is equal to 0, then this will be 0 and this is 0, right? So, at z is equal to 0, limit delta z tends to 0, f of delta z minus f of 0 divided by delta z. This is what we are trying to do to find out the derivative at origin. So when we find the derivative at the origin, then we come to this case. Now in this case, what we do at origin, this delta z, whatever may be the direction you take it, this delta z, right? So this can be replaced with a single z, because the delta z is nothing but this location z minus 0. So delta z is equal to z minus 0. So that's why delta z can be replaced with z. So this case we are put forward here. Limit z tends to 0, f of z minus f of 0 divided by z. So this is how actually we simplify the derivative in terms of z rather than delta z. Clear, Kavya? If this is dependent on m, then the derivative doesn't exist. At least if you can able to prove that there is one path that exists where the derivative dependent on some variable, then actually we say that derivative doesn't exist. It should be unique in all the directions. Yes, we need to verify y is equal to mx. Yeah, for all we need to verify. So can you try to solve this? There are two cases. You have to prove that the function is continuous. The complex function is a continuous function. And the second one is the derivative doesn't exist. Yeah. So the CR equations are satisfied and the function is continuous. Even if you take y is equal to mx line also, so the continuity doesn't fail. The function is continuous and the CR equations are satisfied. Now you can find out the existence of derivative at origin. Everybody got the same thing? The function is continuous. How to verify whether the function is continuous? So you have to verify this function, right? So three cases. One is along delta x, along delta y, and along y is equal to mx line. Three cases you have to identify. In all the three cases, the limit value should come same. Yeah, so that is the continuity case, right? So limit of this function, limit x tends to 0, f of x or f of z is equal to 0, and limit y tends to 0, f of z is also equal to 0, limit y is equal to mx, and then x tends to 0, f of z will come out to be 0. So in all the three directions, this is 0. And at the same time, the function value f of 0 is equal to 0. And the limit value, limit z tends to 0, f of z is equal to f of 0. Hence, the function is continuous. Got it? So this is x tends to 0 and y tends to 0. You take x first and y next. Y tends to 0 and then x tends to 0. You take y first and x next. So I will do one. See this. In this function, limit x tends to 0. Then this function will become, this will be 0, minus y cube into 1 minus I divided by y square. And then these two will cancel out. And then y tending to 0. Then this function coming out to be 0. This is first case. And the second case, you take y tends to 0 first. Then this will become x cube into 1 plus I divided by x square. And x square x cube, x into 1 plus I. So limit x tends to 0. Again it will lead to 0. And then you take the other case, y is equal to mx. And then x tends to 0. That is the third case. Limit y is equal to mx. And then x tending to 0. Here, if you put that value, 1 plus I into m minus m cube into 1 minus I divided by x square. So x will come out and then 1 plus m square. Again, if x tends to 0, there is a factor of x here. This x will make the function value to be 0. So the limit value, whatever may be the direction we approach, it is always coming out to be 0. The function value at that point of origin is again 0. Hence, the limit value and the function value being the same, the function is continuous. Got it? Yes, you can do that. So ideally, we should be doing all the cases because there are infinite number of possibilities that we can approach the origin. Y is equal to mx or y is equal to mx square or y is equal to mx cube plus mx or whatever may be the value. Whatever may be the path you follow, if the curve is passing through origin, the limit value needs to be satisfied at that point because we cannot find out all the infinite conditions. That's the reason we limit ourselves to y is equal to mx and x tends to 0, y tends to 0 or delta x tends to 0, delta y tends to 0 and y is equal to mx and delta x tending to 0. These are the three minimum mandatory conditions. This is a little extension from the CR equations but not 100%. Got it? To find out whether the existence of the derivative is there or not. So ideally we should be considering all the things. Because we are not doing that, that's why I said only we are sure 99% that there is an existence of derivative. Because we have not verified y is equal to mx square or mx cube or any other function you can think of. Got it? Yeah, z is x plus iy we always take. So wherever z is there, you can easily think of that is x plus iy. Okay, so take the second part and then try to find out the derivative of. So I hope you verified the CR equations for this. This was given in the exam. So verify the CR equations for this. what is the value dou u by dou x and dou v by dou y? Somebody tell me what is dou u by dou x and dou v by dou y? These should be equal anyway. No, it's not correct. It's not 0. This is 1 exactly. Check summary. Similarly, dou u by dou y is equal to minus dou v by dou x, and this value is equal to minus 1, I think. Dou u by dou y is equal to minus 1, and the same thing is equal to minus of dou v by dou x. So these are the values. The CR equations are satisfied because these two are the CR equations. So ideally the function derivative should exist, but we are not sure because we have not checked all the 100% curves. Now the derivative to exist, limit z tends to 0, f of z minus f of 0 divided by z. So this is what we need to prove. So f of z value is there. Now take one particular case wherein limit y is equal to mx path and x tending to 0, and this is f of z can be replaced with x cube into 1 plus I minus y cube into 1 minus I divided by x square plus y square into x plus iy. Now y is equal to mx, you replace it, and then here x square and here x, it will come out. So x cube will cancel out from the top and bottom. Limit x tends to 0, then this is 1 plus I minus n cube into 1 minus I divided by 1 plus m square into 1 plus mi. Now if you notice, this is independent of x but is dependent on m. That means this value is dependent on m. So here what we are trying to find out is dw by dz, which is nothing but the derivative. Now derivative value has to be unique always, otherwise we say that derivative doesn't exist. So this value is no more unique because it is dependent on m. That means whatever the path you follow, for each path you are getting a different derivative, which is not true. So the CR equations are satisfied, but the derivative doesn't exist. Got it? Clear? Do you have any questions on this? Any questions on this? Find the CR equations in polar form. Can you try on your own? Find the CR equations in polar form. You try on your own now. The answer? Got it or not? Okay. So f of z is equal to u plus iv. Same thing can be written as f of x plus iy, or this can be written as u plus iv is equal to f of r e power I theta. So this is the polar form representation of the complex function. Got it? So here, if you put it on xy plane, this is x-axis, this is y-axis, and this is a random complex point. the location is x plus iy. The same thing can be written in polar form. This value is r and this value is theta. Then z can be represented as r into e power I theta. Now from this equation, if you take the derivative with respect to r, dou u by dou r plus I times of dou v by dou r is equal to, with respect to r we are doing the derivative. Now f dash of r into e power I theta and then derivative of the inside function with respect to r into e power I theta. This is one case. Similarly, if you take dou u by dou theta, so derivative of this is f dash of r into e power I theta and then the derivative with respect to theta, this is r into e power I theta, derivative is e power I theta into derivative of e power I theta, derivative, right? So into I. So ri into e power I theta. Now this can be replaced with f dash of r into e power I theta into e power I theta can be replaced with dou u by dou r plus I times of dou v by dou r into IR. Now if you equate the real and imaginary parts, this is minus r dou v by dou r plus I times of r dou u by dou r. This value is equal to dou u by dou theta plus I times of dou v by dou theta. Got it? Do you have any questions till this point? The corresponding terms are obviously equal. So if you equate these two, you will get the CR equations. That is, dou u by dou theta is equal to dou v by dou r into minus r, or dou v by dou r is equal to minus 1 by r times of dou u by dou theta. This is equation number 1. And the other equation is dou u by dou r 1 by r times of dou v by dou theta. These are the CR equations. You should try it. I have solved almost more than 50% of the problem, Hitesh. Try on your own. You are going to get it. So dou v by dou r is equal to minus 1 by r into dou u by dou theta, and dou u by dou r is equal to 1 by r into dou v by dou theta. These are the CR equations in polar form. You can note down this. So is this the confusion for you, Kavya? Sorry, yeah, Samrin. Okay, see this. Dou u by dou theta, I times of dou v by dou r. Now here what I have written is, this is f dash into r e power I theta into e power I theta in bracket, and I kept it IR. The same thing I have rewritten there. Now this part is nothing but, this is what I have written. So this is dou u by dou r into I dou v by dou r, I have replaced it here. Now when I multiply with IR, then this is I into I is I square, which is equal to minus 1 into r into dou v by dou r. So this is minus 1 into dou v by dou r, I have written first. Why I have written first is, the convention is to write the real part always at the first and the imaginary part always at the next. Now if I multiply with I here, so I into r into dou u by dou r, I have written it here. Got it? Clarity, Samrin? Now actually you equate the corresponding terms, both real terms and both imaginary terms. So you arrived at the CR equations in polar form. Note down this. Let me know once you are done. Dou square u by dou r square plus 1 by r into dou u by dou r plus dou square u by dou theta square equal to 0. Can you try proving this from these two relations? Other than Kavya, anybody else got? This is straightforward. See this? Every value is u here. Now from this relation, you keep dou u by dou theta one side. I take this one first. Dou u by dou r is equal to 1 by r times of dou v by dou theta. Now if I take the derivative with respect to r again, dou square u by dou r square is equal to minus 1 by r square into dou v by dou theta plus 1 by r times of dou square v by dou r dou theta. So this is equation number 1. And then the second equation, this is dou u by dou theta is equal to minus r into dou v by dou r. Now dou square u by dou theta square is equal to minus r into dou square v by dou theta dou r. Now for all practical purpose, these two are one and the same. So this is equation number 1 and this is equation number 2. From 1 and 2 you can add it and arrive at the relation. Got it? Or do you have any questions on this? This is 1 by r square. Check it. Yeah. Dou square u by dou r square plus 1 by r into dou u by dou r plus 1 by r square into dou square u by dou theta square. See this. There is nothing new I have done here. Just take this relation from the CR equations, dou u by dou r is equal to 1 by r into dou v by dou theta. Now from this you take the derivative with respect to r so that you can get the value of dou square u by dou r square, which is the first part. Dou square u by dou r square is equal to derivative of the first function. UV rule you are applying. 1 by r is a function of r. So dou square, so this is minus 1 by r square into dou u by dou v by dou theta plus 1 by r into dou square u by dou theta dou r. Got it? Got it or not? This is equation number 1. And the second equation is dou u by dou theta value. So dou u by dou theta is minus 1 by r I have brought to the other side. Dou u by dou theta is equal to minus r into dou v by dou r. Now this is dou square u by dou theta square is equal to minus r into dou square u by dou theta dou r. Now from this relation, see this, what you want to calculate is, this is 1 by r into dou square u by dou r dou theta. Now what I will do is, I will divide with 1 by r square on either sides. Then this will be 1 by r square into dou square u by dou theta square is equal to minus 1 by r into dou square v by dou theta dou r. This is equation number 3. I just divided either sides with r square so that I have got this term. Got it? Now this term I got it, this term I got it. Now I will add these two terms together. Dou square u by dou r square and 1 by r square dou u by dou theta. Dou square u by dou r square plus 1 by r square times of dou square u by dou theta square is equal to, now this is minus 1 by r into dou square u by dou theta dou r. This is 1 by r into dou square u by dou r dou theta. These two are one and the same. This part and this two part being equal and opposite will cancel out together. Got it? Yeah. Now what is left over is minus 1 by r square times of dou v by dou theta. Minus 1 by r square dou v by dou theta. This is what is left over. Now minus 1 by r square dou v by dou theta. So plus 1 by r dou v by dou theta is nothing but dou u by dou r. No, now you can replace with this is minus 1 by r into dou u by dou theta. Sorry, dou u by dou r. So this value from the second part of this CR equations, I have brought that relation. Minus 1 by r square into dou v by dou theta can be replaced with 1 by r into minus 1 by r into dou u by dou r. Got it or not, everybody? Yes or no? Then actually you can bring this to the other side. So this is dou square u by dou r square plus 1 by r times of dou u by dou r plus 1 by r square times of dou square u by dou theta square is equal to 0. That's it. Here. Any questions on this? Any questions on this? Harmonic functions. This concept is if two functions satisfy the Laplace equation, then the functions together are called as harmonic functions. Harmonic functions. Here the CR equations, what we have defined is dou u by dou x is equal to dou v by dou y. Similarly, dou u by dou y equal to minus dou v by dou x. These are the CR equations. Now I take dou square u by dou x square and dou square u by dou y square and then try to add it together. That is dou square u by dou x square is equal to dou square v by dou x dou y. Similarly, dou square u by dou y square is equal to minus dou square v by dou x dou y. Now if I add it together, dou square u by dou x square plus dou square u by dou y square is equal to 0. This is what we shortly known as del square u is equal to 0, and this is what is called as the Laplace equation. Similarly, if you do the same thing on the other side, instead of u, if you take it on v side, again it will come as dou square v by dou x square plus dou square v by dou y square is again equal to 0. So this is also satisfies the Laplace equation del square is equal to 0. These two are the harmonic functions. But we know the fundamental function w is equal to f of z is equal to u plus iv. Now here u is also satisfying the Laplace equation and v is also satisfying the Laplace equation. Such kind of functions usually are perpendicular to each other. U is perpendicular to v. So this is the fundamental nature of a harmonic function. Got it or not? Got it? So these two are perpendicular to each other. This has got lot of applications, almost infinite number of applications we got just because of the simple reason these two functions are perpendicular to each other. Especially this analysis is very much needed for fluid mechanics. And electric fields and thermodynamics, whatnot. So many applications are getting satisfied just because of this nature of the functions. U is perpendicular to V. So the analysis of this kind of thing we called as potential theory. So this potential theory has got, so in fluid dynamics we have a specific chapter dedicated to this potential flow. So in the potential flow we are just using this concept U is perpendicular to V. So this U and V, why we have got that much of importance is, suppose U being the equipotential line. Equipotential line we mean, suppose if I take this particular chalk piece, this chalk piece at certain height H1, then if I take one more height, that is H2, then in between these two there is a potential energy difference. So that means the potential at this point versus the potential at this point is completely different. And if I take at the exactly same height level, wherever I go, it will be the exactly same potential energy will be there. So these lines are treated as equipotential lines. That means this is at H2 and this is at H1 and this is at H0. Now at three different heights, three different potential energies are there. Now if there are three different potentials, obviously this chalk piece will try to move exactly perpendicular to the potential difference. That means if I leave this chalk piece, it will go to the directly onto the ground, cutting these equipotential lines together, right? So that's why if you notice these two are perpendicular to each other, which essentially means that if a function represents these lines u of x comma y, definitely there will be an associated function v of x comma y, which will be exactly perpendicular at every point to the equipotential lines. These lines are called as the streamlines in case of fluid flow. So if this is u, this will be v. If this is u, this will be v. So the harmonic function nature of the function will give us a flexibility that if you know one function, you will be able to derive the other function automatically without knowing any information about that. Got it? This is the greatest advantage of this harmonic function. So any function which will satisfy the Laplace equation will possess a counter function. That counter function will be exactly perpendicular to each other. So with the help of, without knowing any information, with the help of Laplace equation, you will be able to derive many things. Yes, because of this perpendicular nature of the two functions which we call as the harmonic function. You can note down this. Now we have this function u, let us say u of x comma y is equal to constant. Then if you take the derivative of this, dou u by dou x into dx by dx, with respect to dx I am taking, plus dou u by dou y into dy by dx equal to 0. So this dx will cancel out, and then dy by dx is equal to minus dou u by dou x divided by dou u by dou y. This is, let us say, m. Similarly, or m1. This is slope of u1. Similarly, if I have the other function v of x comma y is equal to nth constant a, then if I take the derivative of this, dou v by dou x plus dou v by dou y into dy by dx is equal to 0. It implies dy by dx is equal to minus dou v by dou x divided by dou v by dou y. So this is, let us say, m2. Now if I take the product of these two, that is m1 into m2 is equal to dou u by dou x minus dou u by dou x divided by dou u by dou y into minus dou v by dou x divided by dou v by dou y. Now apply CR equations on this. Now, if you apply CR equations, dou u by dou x is nothing but dou v by dou y. These two will cancel out. And dou v by dou x is equal to minus dou u by dou y. That means these two with minus will cancel out. So whatever left over is just minus 1. So m1 into m2 is equal to minus 1. This is exactly the reason why u and v are parallel. So u and v are always perpendicular to each other. Got it? Understood or not? These two are always perpendicular to each other. Do you have any questions on this concept? So this proved us that these two functions are perpendicular to each other, or the conjugate functions. Now, based on this understanding, we see the application of this concept for fluid flow. This I am here itself discussing that fluid flow analysis. Let us consider an irrotational and incompressible fluid. Irrotational and incompressible fluid. That means if you take the fluid velocity, del cross V is equal to 0 and del dot V is equal to 0. These are the two conditions. This says that irrotational. These two are vectors anyway. Irrotational. This is incompressible. Now let us say V is equal to Vx into I plus Vy into J. So this is the velocity vector, and velocity vector being del cross V is equal to 0, that is irrotational. Hence V can be expressed as V is equal to del phi. This is what we call as the potential theory. Where phi is the potential. This is the potential. So V can be expressed as del phi. Now, if I express a two-dimensional del phi, V is nothing but dou phi by dou x into I plus dou phi by dou y into j. So dou phi by dou x into I plus dou phi by dou y into j. That is nothing but V. But V is, again you can express as Vx into I plus Vy into j, where this is the horizontal component of velocity, this is the vertical component of the velocity, which essentially means that Vx is equal to dou phi by dou x and Vy is equal to dou phi by dou y. And then one more thing, del dot V is equal to 0 because it is an incompressible fluid. So for an incompressible fluid, the divergence will be vanish. So del dot V is equal to 0. Hence, if you apply del dot Vx into I plus Vy into j, this is equal to 0. So this is dou Vx by dou y, dou x plus dou Vy by dou y is equal to 0. So if you apply derivative on this, then this is dou square phi by dou x square plus dou square phi by dou y square is equal to 0. So this is again the Laplace equation. So as the Laplace equation satisfies the potential function phi, there will be a conjugate that exists for that particular function. W is equal to phi of x comma y plus I times of psi of x comma y. This is the conjugate function. Why we have assumed that this conjugate function is because the phi is satisfying the Laplace equation, which we say the harmonic function. So the harmonic function will always tend to give a result that there will be an existence of a counter function which is conjugate to the potential function. Clear? So if this is the potential, then this will be automatically stream function. Stream function, we mean the fluid flow directional flow. The fluid flow direction field lines, if you draw it, that's what we call as the stream lines. And this is the equipotential lines. Got it? So this kind of analysis is called the fluid flow analysis. So if you notice, everything we brought it from vector calculus and complex analysis, nothing more than that. This is what we are going to do it in the upcoming classes. Yeah, it is fluid dynamics, exactly. So here, one important application of fluid dynamics, we have derived it here. That is, we have defined something called potential function. That potential function satisfies the Laplace equation. If the function satisfies the Laplace equation, automatically there will be a harmonic function that exists, which is exactly perpendicular to the potential function, which we say that the stream function. Got it? So these results we have got from the principle of complex analysis and the vector calculus. We have considered one flow, that is a specific kind of flow where it is irrotational and incompressible fluid. Got it? So in the vector analysis itself, actually I have clearly explained what is an irrotational flow and a compressible flow. So incompressible flow, right? So these two actually I have explained when I dealt with the vector calculus. So almost 50% of the vector calculus actually usually I cover at vector calculus and complex analysis. There itself I cover almost 50% of fluid dynamics. Rest of the thing anyway I will take it during there. Got it? Potential function, right? So potential function is nothing but the equipotential lines function, right? As I said earlier, suppose if I take this chalk piece, potential function is nothing but a potential energy function. So if I take this chalk piece at this height level, everywhere it will possess the same potential energy wherever the location I take it at the same height level. And this plane is called the equipotential plane, correct or not? Got it? Currently, yeah. So this is the equipotential plane. Now exactly in the similar manner, this is phi of x comma y is equal to constant. We mean this constant is nothing but the potential value which is there on this plane altogether. Suppose if I change this constant to C1, which means I came down to another height, wherein if I draw one more plane at the different height, the potential is exactly constant at every point on this height. But this will be a different value C1. Got it? So all these lines together, you can generally assume that phi of x comma y is equal to constant. And phi of x comma y is equal to constant is nothing but a equipotential plane. Got it or not? So if there is a equipotential plane, then from the basic result of vector calculus, for an irrotational flow, del cross V is equal to 0. That means there are no curls in the flow. Curls means there are no rotational swings there. So the fluid flow is continuously moving like this. There is no rotations everywhere. Got it or not? So at every location there won't be not even a single curl. Right? Curl means rotational nature of the flow. If there is no rotational nature, then for such kind of flow, the velocity, if you take the curl, del cross V is coming out to be 0. If del cross V is equal to 0, V can always be expressed as a function of del phi. So that's what I have done. V is expressed as del phi if del cross V equal to 0. Got it or not? If del cross V is not equal to 0, then you cannot express this. So this is these two constitute very, very important result. That resultant is, this makes the fluid dynamics analysis completely divided into two different formats. So the fluid dynamics subject itself is divided into two different formats just because of this simple reason. If there is a curl, the analysis is completely different. If there is no curl, the analysis is completely different. If there is no curl, then the analysis is completely easier. So that's what we call as the potential flow analysis, or the potential flow in short. So if del cross V is equal to 0, V can be expressed as del phi. That is dou phi by dou x into I plus dou phi by dou y into j. If this is the case, V value I have expressed in terms of a potential function called phi. So if I could able to express phi, right, for V, then del dot V is equal to 0 is one more important example. Del dot V is equal to 0 means it's an incompressible fluid. That means you cannot compress the fluid. So if you cannot compress the fluid, then the continuity equation is valid. So continuity equation means the fluid, whatever is entering the room, it has to go out always, because there is no compressibility within this particular room. Whatever the fluid that is coming inside the room, this room fluid has to go out the same quantity, correct? So that such kind of flow is called as incompressible fluid. So del dot V is equal to 0. From these two relations, V I have expressed as del phi, and I substituted here, it is coming out to be del square phi is equal to 0, which we say it is a Laplace equation. Earlier, just in today's class, I proved that the Laplace equation is getting satisfied for a complex function, which is expressed as u plus iv. So for u, it is the Laplace equation that is satisfied, and even for the v also, the Laplace equation is satisfied. And these two functions we always treat as conjugate functions or the harmonic functions. That means for any two different sets of conjugate functions, if you know one function, you will be able to find out the other function. Got it? So here we got to introduce one function called potential function of phi, and for that we proved that the Laplace equation is satisfied. Then automatically we can state that there will be a conjugate function called psi. If this is a potential, automatically there will be a stream function that exists for it. Got it or not? So our analysis of fluid flow, what states is the potential fluid will be given, and you have to find out the stream functions. Some of the problems are based on that. So this entire analysis is called potential theory or the potential flow analysis. Suppose if this is not equal to 0, then there will be curls that are existent. Curls, we mean the fluid is not going straight forward like this. So it rotates and moves like this. Then such kind of flow cannot be expressed as the potential function. That analysis is completely different. It is much more complex than this. Got it? Any questions on this? Okay, so with this I'd like to conclude. So this is the complete analysis of fluid, complete analysis of application of complex functions for the fluid flow applications. So in tomorrow's class, I'm going to discuss how to find out if you know one function, other function, how we can find it out. For any analytic function, we'll be finding out such kind of cases, which I'm going to deal with tomorrow. Clear? After that, we'll be dealing with the complex integration. So if you have any questions, you can let me know. Any questions? Yeah, so that's all for today. Yeah, thank you. Good night.